But
West Point Bridge, or West Point Optimal Bridge Designing. Lead designer, me, Kai Baker. Alright, so bridge number 1, design brief. The clientele company is going to be the Urban Engineering Department. And the consumer for this bridge is going to be the drivers that drive across it. Problem statement, I need to design a bridge that is stable enough to stay stable given a list of criteria provided by the statement. Design statement, a bridge under $200,000 that follows the city code and transportation laws and size constraints. I'm not going to read all the criteria and constraints, but if you really want to, you can always look through that. Design pictures, we've got a couple of the pictures here of the design. It goes very low into the valley, slightly above the high water level, but it still stays above that, which meets the design constraints. Design summary. The bridge was designed using materials that would minimize the total cost of construction and follow suit. The 2 top member bars are made of high-strength, low-alloy steel with a dimension of 120 by 120. These are the 2 most solid points of the bridge, which are there to maintain the rigidity of the bridge under stress. The other trusses / members in the bridge are made of 160 by 160 by 8 hollow tube, high-strength, low-alloy steel. These are cheaper to make, however, still maintain a good level of strength. The members on the bottom of the bridge are made of solid bar, high-strength, low-alloy 75 by 75 steel. There's not nearly as much stress on the bottom of the bridge, which allows us to utilize a smaller, cheaper material. Using cost calculation report, we are just under the mark of $200,000, sitting at $198,000 total, as you can see.
198. Is that what you said?
Yep. It's the load test animation. As you can see, I made it very optimal. It just kind of bends just a little bit. That's optimal. And it is follows constraints with the truck. Bridge number 2, design brief. Once again, the Urban Engineering Department requests me to make a very expensive bridge, with the target consumer being the drivers that drive across it. It must stay stable enough to stay stable, given a list of criteria provided by the state. And the design statement is a bridge that does not have any budget constraints, but must follow the given criteria. Very similar to the last bridge. Here are the design pictures of the bridge. It is much higher up in the valley that allows it to stay over the water level, or higher than the water level, just in case, water levels change, climate change and everything. Made of very, very strong materials and very solid materials. Design summary is the bottom members of the bridge are all made out of solid bar 500 by 500 carbon steel. This is to keep the maximum amount of strength on the bottom, which creates the least amount of deflection for the concrete to risk cracking on the surface. The surrounding members use the same solid bar 500 by 500 carbon steel. Doing this keeps a cage-type frame that also reduces the amount of deflection on the bridge surface to reduce the cracking of concrete. By doing both of these, it significantly improves the lifespan of the concrete, saving more money and longer. The other members within the bridge are made of the same solid bar carbon steel, but a smaller 300 by 300 dimension to allow for it to not look incredibly ridiculous, as well as the fact there's no reason for them to be as strong as the top members. Here's a cost calculation report, just a measly $3.7 million. That's fine, it's light work. And there's the load test animation for the bridge. See, it is very, very stable and strong.
All right.